Can you hear me? Can you hear me well? All right. So the first question, do we have any non-Polish speakers with us today? All right, so I'll keep it in English. Right, so the topic of today's presentation, yeah, you see it on the screen. And I would like to talk not really about what kind of sandboxing solutions we have today on the market, in the Linux kernel, in external projects, but really when things can go wrong. It all started with this Twitter retweet, multiple speed bumps don't make a wall. It was coined during this antivirus saga, which is going on right now on the Twitter, when the antivirus makers are not really sandboxing, they're antivirus parsers. And those parsers are very complex, usually parsing things like PDF, documents, unpacking many things. And during that discussion, when somebody said, okay, but we enabled something like ASLR for our parsers, somebody said, okay, but like hardening is not really sandboxing, right? You cannot just simply enable hardening here and there and say that your parser is safe right now. So I would like also to say that I'm speaking here in my own name. Please do not attribute my talk to my employer, to my friends, to my dog, not that I have a dog. And why we would like to sandbox things in Linux. So we can start with things which we think are relatively safe, like image converters, right? But when you look at the recent history of fuzzing of those, there are multiple bugs in image converters, video converters, PDF parsers, any kind of parsers that you can think of. So if you have a company which is displaying videos on your web pages, and you want to convert one video to your custom format, for example, somebody submits AVI video or any other format, and you want to convert it to some common format, you will probably use something like FFmpeg, right? Because it works. But there are problems with such things. There are at least 1,000 bugs that Mateusz Jurczyk, who introduced me, reported in the recent years in FFmpeg. So using FFmpeg is probably not the best idea to convert untrusted inputs. But what else, right? Anything else is equally broken. So why not use some kind of sandboxing? Yeah, so we need to use sandboxing for this kind of things. It's also probably good to use sandboxing or some kind of sandboxing facility for services which are thought to be reasonably good in terms of quality. Things like Apache or IAC-Bind. If not for security that somebody will get remote code execution, maybe it's even good for resource limiting, right? We don't want for somebody to find a memory leak in Apache and then eat up all our memory and we are left with a server which doesn't work. Cloud and VPSs, this is a separate topic. But I would like to mention to you that in Poland, at least, I'm sure around the world as well, there are companies which are offering services for people who want to hire engineers, software engineers. They are giving them programming tasks. Usually it's write something in Java, write something in C++ that solves this kind of problem, right? So people are submitting their binaries or source code, and it's some kind of classification platform which actually compiles their code or runs their code and checks whether it actually works, whether the software engineer is worthy the job that we are trying to propose to them. And I know of Polish companies which are providing such services. So if we want to compile somebody else's code, this is not a very wise idea, right? The source code, for example, for C, allows to including arbitrary files. What is more, if you add assembler includes inside C code, you can also include arbitrary file, and that file will be embedded in your binary. So sandboxing is basically a must for this kind of things when we are executing the code or source code, compiling the source code which was produced by somebody else. Also capture the flag competitions. The capture the flag for this conference has just ended. Congrats to the winners. And obviously we need some kind of sandboxing as well. We usually don't have as many servers as there are tasks given to them to the competitors. So some tasks are running on the same computer. So we need some kind of isolation between them. Otherwise, if somebody breaks one of our challenges, that person can then else go to another challenge and steal the flag and gets the point that shouldn't be awarded to such person. And we have also those higher skill security engineering things like malware research, dealing with antiviruses or stuff, and reverse engineering, which we are trying to find out what unknown code is doing. So yeah, sandboxing is a must for many things these days in Linux world. But let's think about it. So let's assume that we are executing some unknown payload. It could be a piece of malware, it could be a piece of binary which was provided to us by somebody who is our hiring pipeline, and we execute it for somebody. And we are good engineers, so we are doing some security assessment, and it turns out that we can apply some kind of sandboxing around it. So first of all, we harden the runtime, we enable ASLR, PIE, non-executable stack cookies, and so on. Then we think, okay, that's not enough, hardening is not enough. Let's apply some kind of sandboxing. So we use seccomp BPF or maybe ptrace, this and that. Okay, so we are right now sandbox. Let's set up the system itself correctly. In case somebody breaks out of our sandbox, we want to make sure that that person will not leave the account permissions that that person has on the system, right? Then we are hardening the kernel, applying security patches like GRSec or PAX, or disabling functionality which is not required for our sandbox job. But then, let's see. So this payload is actually executing on a hardware, right? On a CPU. And CPU is not sandbox, it's not hardened, nothing like that. So in the past, there were cases in which really adequately sandboxed payload escaped the whole sandboxing chain just by the fact that it was able to touch either CPU or graphics driver. That's the cases I know. So about escaping this kind of sandboxing via CPU access, I will tell you a bit more later. Or for GFX driver, I believe in Chrome OS, Pwn2Own, or Pwnium competition, there was one escape in which the contestant was able to use basically direct connection to the graphical driver inside the kernel and bypassed all kinds of sandboxing which was applied to it. And I guarantee you that Chrome and Chrome OS has really good sandboxing. So for the case of escaping sandboxing, really strong sandboxing by the flaws in the CPU, this topic was brought up a couple of years ago, and it gets more and more interest from various researchers. I found this bug over a year ago. So this bug allowed to escape from unprivileged account in a virtual machine into the ring 0 of the host machine, right? So one more time. So we are totally unprivileged inside VM running under QEMU, under KVM. And by using special facilities of the CPU, we're able to execute code in ring 0 in the kernel, not of this VM, but on the host machine. So yeah, so when we think about sandboxing, we really need to make sure that what we are applying around our payload, around what executes, is really a layer. That's not something which is bypassable by the fact that we have direct connection to other facilities which are beneath, like CPU, right? It's really hard to avoid CPU bugs, but, well, we can at least try. So the first thing, which is not obviously sandboxing, if you worked with development of software on Linux, you probably heard about various things that people tell you to enable in order to achieve better resiliency against attacks. So we are talking about things like randomization of the virtual address space, applying stack protectors, which will add cookies to your stack, so it's not as easily, buffer overflows on the stack are not as easy to be exploited. There are certain facilities in the kernel, like Fortify Source, you can read about them. They're kind of good. I mean, they add complexity. They add only a little bit of complexity to your binaries, so the attack surface is not increased, but they offer really good protection, right? They offer really good protection against typical bugs. But these are bypassable. If you have memory leaks, arbitrary memory leak, you cannot do anything about protecting your binary with stack protector, stack cookie, right? You can basically leak the cookie and then execute your code. There's another category of hardeners, or maybe these are not hardeners. You probably have heard about things like address sanitizer, memory sanitizer, and undefined behavior sanitizer in Linux. These are things which are used for software testing. And they are really, really awesome when you want to find out whether your software has some kind of memory problem. So address sanitizer can tell you whether you have buffer overflow on the stack or on the heap, and a memory sanitizer can tell you whether you are spilling out or using basically memory which hadn't been initialized previously. And this is really awesome. In conflation together with fuzzers, those tools had found thousands of bugs right now. You've probably heard about projects like AFL or libfuzzer or HonkFuzz. So adding address sanitizer is a must. It will find so many bugs. But some people say, okay, so if it can detect buffer overflow or overflow on the heap, why not just apply it to our binaries, to our Apache, to our bind, and just expose it to users? But it's not a good idea. Those facilities weren't written in security in mind. I mean, not with security of protecting the binaries against untrusted attackers. They are awesome detection tools. But on the bottom, you see an example in which a binary, which is Setuid binary, which was compiled with ASAN, can be simply used to gain local privilege escalation, right? Like ASN libraries don't check whether the binary itself is Setuid. They will write to wherever you want. You can write to etc pass wd, whatever, right? So let's go quickly through the legacy mechanism, just to underscore that they still exist. So we have things like limit C groups. They can be used for resource limiting, like how much given process can use memory. Well, there's no even such limit. There's a limit which says how much address space it can allocate, right? But these are not, we shouldn't consider them sandboxes. They also are not cumulative in terms of limits. So if we spawn another process, new limit will apply to that. C groups are a little bit better, but let's keep that. So the first mechanism, which was basically used to do some kind of isolation of running internet servers, was Chroot. It was used with, I believe, with SSH. It's still used probably with ISC bind. But Chroot is not a very good isolation mechanism. Chroot suffers from many problems. It can be used only by root. It's bypassable. On the bottom, you are seeing a code which allows you to escape Chroot, and this code is there by design, which means like authors of the operating system are not even trying to prevent this use case. If you ever worked with computer security, you probably recognize this kind of code. Also, with the new security facilities in the Linux kernel, namely namespaces, it's possible to escape Chroots. On the bottom, you are seeing some flags to Linux syscall calls to make it happen. About that a little bit later. But when we are Chrooted, what you can do, you can ptrace to any process that you that runs with the same privileges as your process outside the Chroot, right? And when you ptrace something in Linux, it means you have total control over such process. So you can inject your code, whatever you want, right? The same you can do with process vmwrite-v. It's kind of new syscall in Linux. And similar thing can be done with things that Chroot doesn't isolate. And Chroot only isolates your root of your file system. It doesn't isolate you from, for example, networking context in the system, right? You can still access, for example, abstract namespace. Well, it's kind of quirky thinking in Linux, but you can, for example, connect to something like udevd or cron daemon, which are exposing those abstract sockets, and ask them, hey, can you execute some kind of code for me? And, well, if you find such kind of broken implementation, those services will execute code for you, which is not Chrooted. So Chroot is not good. Yeah, and in terms of shrinking the kernel attack surface, it only shrinks it minimally. You can probably exclude things like devices from your path. Well, dealing with devices is probably one of the easier ways to get remote, privileged escalation in Linux, because devices are usually based on drivers, and drivers tend to be buggy. And throughout this presentation, I would like to apply this Futex test to all the sandboxing facilities that I'll be talking about. So in 2014, there was this kind of famous bug in Futex. And it's kind of interesting because Futex is kind of basic syscall. It allows Linux processes to implement mutexes across threads and processes, also some conduits and similar things. So people were kind of surprised also by the fact that Futex is required by so many things in Linux. So when you have multi-threaded process, the C library in Linux will use Futex to implement mutexes, right? So you need to allow mutex. You need to allow Futex in your syscall policy if you use multi-threaded processes under Linux, in most cases. And I would like to test whether each of those sandboxing facilities are able to block single Futex syscall to prevent this kind of bug from happening. Okay, so something which also cannot limit the Futex problem and this kernel privilege escalation is capabilities. Capabilities were probably the first, maybe introduced along truth, ways of trying to limit what a process can do. So when you run ping on Linux, the bin ping command is set to it, right? So it runs with root. But immediately after starting, it drops its capabilities, and the only capability that it retains is ability to create row sockets, right? Because row sockets are required to create ICMP messages that ping is using to send ping messages. So it works here, but it didn't caught up. People are not really using capabilities. It's used in a couple of projects, but it's really problematic. First of all, it's messy. Right now, it's maybe 60, maybe even 70 different capabilities that were introduced. It's really hard to remember what they all are doing. The other problem is that capabilities are sometimes root equivalent by design. So we are having this cool capability, which is called capsys_truth, which allows you to use truth. And as I explained in one of the previous slides, ability to do truth is root equivalent, right? You can, well, okay, so it's on the bottom. So if you are able to do truth to arbitrary directory, you can become root. It's because you can link set to it binary into your directory, then truth, then put libraries that Binsu is using, but this will be your libraries. So whenever Binsu will use whatever you want, I don't know, printf, you can implement code in printf in such libraries which will do, something with the root privileges. So the problem with capabilities is that many of them are root equivalent, which is probably, I don't know who designed this kind of capabilities in Linux, but it's broken. Quickly over software and CPU emulators. When somebody is executing the code on behalf of somebody else, for example, this binary that a software engineer candidate sent to us, it might seem a good idea to run it in the virtual machine emulator. I'm not talking about KVM, like bare metal emulation. I'm talking about those older solutions, something like QEMU software. But it also probably is not a good idea because, first of all, they are kind of slow because they interpret any instruction of the incoming assembler and writing it to the native assembler. With just-in-time compilation, it's a little bit faster, but still the whole thing is suffering from so many bugs over the time. Actually, parsing a binary and arbitrary assembler opcodes is so error-prone that it's guaranteed that if you write something, it will have bugs. And yes, in the past, there were so many bugs in the QEMU, VMware, VirtualBox, and so on. You probably heard about this Venom bug, which is totally overhyped bug. I believe it was something about exploiting driver for the floppy disks in QEMU, I believe, right? But there were, over the course of the last years, there were so many bugs in the VGA adapters, Ethernet drivers, ESB emulations, and Kostya Korczynski, I believe last year, published a bug I don't want to lie to you, but I think it was in VMware in which he exploited the printer service inside VMware to escape from the VMs. So no, do not run arbitrary payloads inside software inside software machine emulators. Okay, so somewhere in beginning of 2000, I believe, ptrace was introduced inside the Linux kernel. It wasn't introduced for security, it was introduced for debugging. So when you fire up GDB, for sure it will use ptrace syscall. So people kinda early figured out that why not use ptrace then for sandboxing binaries. And yeah, it turned out to be kinda good idea. It actually worked. Probably the first implementation, or widely used implementation, is Systracer, I believe the name of this tool, by Niels Provost. And it worked really nicely to syscall individual policies. But it had also some drawbacks. So it was slow, because whenever a monitored binary invoked a syscall, the context switch had to happen, and another binary had to check all those arguments to the syscall. This is slow, right? You can imagine that. The ptrace syscall is very powerful in Linux. Probably, if not the most powerful syscall, it's one of the most powerful syscalls. It can do basically everything to other processes. So the implementation is messy. Between architectures, different architectures, for example, between Intel x86 and ARM, there are so many differences that you need to basically read the kernel source to figure out how to implement your sandboxer. Otherwise, you probably will do it wrong. And on the bottom is just to signalize one interesting bug, which I believe still is in the Linux kernel. There is, you can, to any process inside Linux, if you have proper permissions, you can send skill signal, and then the process will end. But the premise is that the process should end as fast as possible. But imagine that you are ptracing a process that you are trying to police, right? So the PIT, the first process, is your ptracer. Sorry, the first process is the PIT process is the process that we are trying to sandbox. The second ptracer process is the process which applies the policy, and the third process is something that maybe by mistake is sending skill to our traced process, to our ptracer. So we are waiting for the event of syscall, okay? We know right now that our PIT invoked some kind of syscall. We want to check what's the state of register to figure out whether to allow this syscall or disallow this syscall, and then skill comes. And what Linux kernel is doing is just says, all right, I cannot wait for the ptracer to keep my process, my PIT, in the waiting state. I need to kill it as fast as possible, because that's the definition of skill, right? Kill as fast as possible. And it allows the syscall immediately, detaching the ptracer. So if you don't read Linux kernel source code, you might miss such subtle bypasses of the of implementation of the ptrace. So this is another example. We'll probably skip some of those. This is another example where ptracing can go wrong. For example, in early implementation till 2.4, we didn't know whether the event which is coming to the ptracer is actually a syscall or not. So we didn't know, even if it was syscall, we didn't know whether it's entry or exit of the syscall. So we had to have a flag, which is whatever, call it whatever, is entry in here, which was changing with every event from the ptrace process, right? Right now it's entry, right now it's exit, entry, exit. It never changed, right? But what you can do, take a look at right side of the screen. You can introduce software breakpoint with int3. And right now, you will get additional sigtrap event. And your entry exit gets basically messed up, right? You are treating syscall entries as exits and exit as entries, and so on. And only in 2.4, they introduced additional flag, which allowed it to happen. But see how late it was introduced after the first Systracer was brought to the market. So Systracer basically was vulnerable to such simple trick. Other problems with the ptrace. Time of check, time of use. Probably many of you have heard about the term. It's the problem when you have multiple threads inside one process and you police all of them. The problem is that they are sharing virtual memory. And there are syscalls which are taking not arguments in the registers, but pointers in the registers. So if you want to open a file, you don't provide to the syscall the name of the file, right, in registers, because registers are 32 or 64-bit long. You need to provide pointer to the user memory. Now imagine you have two threads at least, right? So what happens is that you are invoking syscall, for example, open, with a file which is allowed, this res.txt. All right, our ptracer here in pink checks that it's res.txt, it can do it with ptrace, and says, okay, let's allow it. But in the meantime, another thread is changing the memory from res to etc passwd. There is not really much you can do when you use ptrace to sandbox your binaries. There is one idea mentioned on the bottom that you can use something called read-only maps with ptrace, but it's so advanced stuff and it's so hard to implement and make it work reliably because it requires injecting additional code into process that it's really not worth doing. So those who implement ptrace sandboxes must live with this kind of problems. Another simple problem, till some time, it wasn't even possible to follow the process. When the process wanted to create a child, the ptracer had to manually change the flag inside, change all forks and vforks into clone syscall with specific flag which is called clone trace. Only since like 2.5, yeah, we have those additional flags in the kernel which allow for that. So you can see nobody thought about implementing ptrace for security sandboxing, but it can be used. It can be used. Okay. This is probably the biggest flaw that was there in the ptrace, which is, okay, you are ptracing some binary, which is executing arbitrary code submitted by somebody else, but for some reason your ptracer dies, right? Maybe the kernel killed it because there was out of memory condition. Maybe you made some mistake and some undefined behavior happened. Well, the ptracer dies. It can happen, right? Or maybe you forgot to police the kill syscall in your process and it killed your own ptracer. Right now, your sandbox process has no sandboxing anymore. Only, I believe, 2 years ago, there's new flag in the ptrace which allows you to kill the process which is sandbox if the ptracer dies. But I'm not sure if everybody using that. Now, okay, it's probably the end of the saga that ptrace is so broken. If you are working on that, you probably figured it out that dealing with signals which are delivered to the process is total mess, and it varies between different kernel versions. And last slide for ptrace is that you can have different syscall tables inside Linux. When you have a kernel which is 64-bit kernel, you can compile an option which says support 32-bit binaries. And those 32-bit binaries are using different syscall table. So when you, for example, are using on 32-bit machine syscall number 1, it means exit. On 64-bit machine, it means write. So when you're using ptracers, you need to be aware of this fact because there is no easy way to differentiate between those two syscall tables. There are some ways to work around that, but these are not perfect. I'm sure those slides will be distributed later. I don't want to make it longer than necessary. So on the bottom, you have some of those ideas how to work around it. But it's not really, there is no legal way of differentiating between syscall kernel tables in use in Linux when ptracing a process. One of the idea which actually works is probably to apply some kernel patch which disallows calling for 64-bit syscall table from 32-bit process and vice versa. But it doesn't come in Linux by default. Okay, so to finish with ptrace, we have another interesting thing which is called native client. It requires total recompilation of your process, and then you have a process which cannot escape the jail. It's totally software-based sandboxing. It's very effective. I reviewed it. I trust personally in it. It's based on the fact that inside one process you have something called knuckle jail, in which specially compiled process, for example, ImageMagick or something like that, can only jump into join points inside this knuckle jail. It's enforced at the compilation and verification time. a couple of neat tricks are used to do that. And in order to communicate with the outside world, because the knuckle jail cannot communicate with the outside world, it cannot call any syscalls, it needs to call into something called, which is runtime service. This is part of the code which lives inside the same process, but it's unsandboxed. And actually, x86 segmentation rules disallow from jumping from outside knuckle jail to anywhere in the process, and only one jump into this trusted stub is possible. So this trusted stub is written by us, and then we can make a decision. Did knuckle jail ask us to do something sane or insane, and then maybe relay this request to the operating system via syscalls. You can probably read a little bit more about how knuckle works. It's absolutely brilliant piece of work. It's based on Raskocz's VX32 idea from 2007, I believe. But generally, in order to preserve the flow of instructions, so you cannot jump into middle instruction or anything like that, you are doing nice neat tricks like in here. So there is no jump in knuckle. There is something called knuckle jump, which is translated to this kind of set of instructions. If you are working with assembler x86, you will notice that you can jump only to the borders of 32 bytes, right? So this guarantees that you cannot jump into middle of instruction, or you cannot jump into middle of function even. But so it's kind, as I said, it's a really awesome idea, but it's really hard to implement it. If you have small scale projects, it's probably not worth it, because you will have to write so much code, because Knuckle doesn't support certain things like JIT or dynamic code or anything like that. Basic C code, basic C++ code will work. Anything else will eat your time a lot. And even if you implement something in Knuckle, maybe it's a good idea to actually apply some syscall sandboxer around, just in case, right? So why it's not good? Yeah, I mentioned that it requires kind of extensive writes of your code in case of bigger projects. And it also depends on the fact that your CPU depends in the same way. So what Knuckle authors are doing, they're only allowing some whitelist of the Intel and ARM instructions, those instructions which are known to behave sanely. But if by any means those instructions will stop behave sanely, or they will be back in the firmware of the CPU, then, well, it's probably Knuckle escape. Yes, that's the idea, right? And this picture presents you what I would consider really, really good sandbox, right? So if you compile something into Knuckle, and with great deal of attention write your trusted stub, so something which actually checks whether your Knuckle is doing reasonable requests to the operating system, and you put some kind of namespace containers or limits and syscall sandboxer around it and put around KVM, and it's good design, I guess. You can even skip the KVM. All right, Knuckle. Seccomp. So there's version 1 of Seccomp. Only 4 syscalls are available. I believe it's a it's a safe sandbox, but totally unusable. You cannot even allocate memory with that, as you can see, right? You can only read from file descriptor, write to file descriptor. You can exit the process, and you can return from signal handler. And people were thinking, oh, that's kind of a great idea. If I have some spare computing resources, maybe you can send me your binary, and I will run it under this Seccomp, right? Because you cannot do anything wrong to your operating system with just read, write, and exit. You can read from standard input, write to standard output. But writing a code which is using only those 4 syscalls is basically impossible. It has been tried. Early Chromium Sandbox used as one of the version of the Linux sandbox this idea. It was the most crazy sandbox that I've seen. There was one process in one thread was Seccomp by Seccomp mode v1, and the other was unsandboxed. And basically, you had to write your unsandbox, this green thread, in so crazy way. You cannot depend on any volatile memory. It was a piece of masterwork, but yeah, I think it was really hard to maintain. And right now, the Linux, Chrome and Chrome OS are not using this Seccomp sandbox. This is quickly one idea. No matter what sandbox you use, if you really nicely sandbox it, you can always ask external process to make decision for you whether you need some resources. So let's assume that you have sandbox v1 inside your sandbox process, for example. But if you have AF Unix socket open with some other process, you can send some request via some simple RPC saying, I want to open this file, right? And this trusted process on Sandbox Broker can make a decision. Yeah, that's really good idea to open this file, and this file is disallowed, and so on and so on. It's possible to create such architecture. SecOnBPF, it was introduced a couple of years ago by Chrome OS people, Will Drury especially. And it uses the idea that it's good to use Berkeley packet filters, which were previously used for assessing what packets, for creating filters for TCP dump inside the kernel, to reuse it for assessing security state of the syscalls. And it's actually possible. You are given such structures, and with simple BPF code, you can actually check whether you want this syscall to be executed or not. So you get syscall number, architecture of the syscall. Remember, I said that there is 32-bit, 64-bit syscalls inside at least Intel. You are given instruction pointer, which is not really used, and arguments to the syscall. Unfortunately, you are not given process ID nor thread ID, so you cannot, for example, implement policy which says send a signal to yourself. It's a pity that it's not there, but anyway, SecOnBPF is very useful. Yes, let's keep that. So the first version of SecOnBPF, well, SecOnBPF worked kind of well from the beginning, but there was no language to describe how those policies look like. You had to use basically naked BPF opcodes, like here. Except a couple of people, I guess nobody would understand what they mean, right? Kind of magic. Especially not for regular software engineer who would like to apply some simple sandboxing around. So people came up with simpler ways of doing that. So there are macros, which are basically translating to those crazy opcodes of SecOnBPF. As you can see, it's kind of readable, especially if you work in security. You can figure it out that we are doing something to syscalls. We are allowing some syscalls, disallowing some syscalls, and with certain syscalls, we are jumping for additional checks to check additional arguments in here. So these are macros. But in order to make it even better, there is configuration language, CAFL, which you can use. It's a configuration language which can be compiled into BPF bytecode and then uploaded to a kernel. And Chromium people came up with the idea of BPF DSL, domain-specific language. You can write your policies in C++. And by the goodies like C++ templating, you can do it in a really interesting way, as you can see on the right. You are using some templates to figure out which arguments apply to which variables. Okay, so SecOnBPF has one big flaw, is the fact that it cannot check userland. So when you open a file, it cannot check what file you are trying to open. You can only check whether it tried to open it read-only, right? Read-only is a flag, it's integer or enum inside Linux. But as a first argument, you are given a pointer to the user memory. SecOnBPF cannot expect user memory, and it's a big flaw. Nobody knew how to implement it in a certain way, but nevertheless, SecOnBPF is very useful. There is also a problem that you cannot really write one policy for all architectures, because the syscall tables, it's not really the fact that numbers of the syscalls differ between different architectures. It's the fact that in Linux there are certain syscalls which are present in one architecture and not the other. There's ArchPHCTL in 64-bit Intel, but it's missing from 32-bit. So if you are writing policy, you need to write a lot of ifdefs. And I was talking to the author of OpenSSH who said that he would use something else than macros if only it allowed it to, like, say, apply this syscall check to this architecture and not this syscall architecture. So if you come up with something like that, let him know, I guess. So namespaces, something as a basis for creating Docker, LXC, and those cool, interesting things. So it's based on a kernel facility called namespaces, which are enabled by flags to unshare syscall or clone syscall. And with the introduction 3, I believe, 0.16, you are allowed to create Docker and LXC containers from simple user, not from root. It unleashed mayhem in the Linux kernel because so much code had become available from the time. Inside such container, you are able to create, for example, row sockets. You are not allowed to create row sockets when you are a regular user. But inside your container, it was thought to be safe. Okay, it's conceptually safe, but the implementation of the row sockets for so many protocols is broken that it led to so many kernel privilege escalations inside the Linux. And it happened for a couple of years. Here's one example which no longer works, in which you are able to become root on your machine. It works for a couple of version of Linux. So basically you were able to root a process, and I told you ability to root a process is equivalent to being root, right? You can provide your own libraries. So you have two threads. One is entering the namespace. It's able right now to root your process. The root is an attribute of the whole process, not the thread. The whole process is now rooted, but one of the threads is still in the main namespace. It executes as soon as you become root. Yes. And it doesn't really shrink the kernel attack surface. So the fulltext problem that I told you about, namespaces doesn't do anything about restricting the Linux syscall table. But if you combine some of those facilities, like if you have your payload, which is sandboxed by a syscall whitelist, either implemented by ptrace or seccomp-bpf, and you apply NS containers around of that to limit what kind of file system you can use, what files you can use, what kind of network connections you can use. And around that, if you apply resource limits, then it constitutes kind of good sandbox. You can both limit syscalls, you can limit syscall arguments because namespaces provide you that. So yeah, it's kind of usable. Basically, the last thing is all kinds of KVM these days. KVM is ability to use directly computing capabilities of the underlying CPUs, of the host CPU, and you can see in here that this payload, which is untrusted process, can use some part of the CPU, but it's not the only point of connection to the system. That process can also needs to be serviced by host kernel for emulations of some CPU instructions. It also needs to be provided with certain facilities from the monitor, from the supervisor. The supervisor will give access to the devices, to the file system, to the networking, to serial ports, and it's a big attack surface. So it's basically pwnable, right? There are other things that you can maybe read about in your spare times, but they are not also passing the fulltext test that I described about. That's the last slide. So basically what to use if you want to really sandbox something which is coming from external users and it's possibly arbitrary and hostile. So obviously not error limits, not root, not capabilities, nothing like that. ptrace, if you know what you are doing, you can implement Sandboxer. Seccomp, nobody implemented anything interesting using Seccomp v1, but it works. Seccomp-bpf, yes, that's good. Native client, really hard to write something for native client, but it works. It's isolate you from the system. Linux security modules and new things like Capsicum and don't isolate you, right? They either provide group of policies or limit you from doing certain things inside the kernel. And yeah, that's basically it. The idea is that you really need to know what you are doing if you want to write a sandbox for Linux, because it's full of corner cases. Thank you very much.
Thank you very much.